It's my pleasure to introduce Professor Siddharth Parameswaran from Oxford. So Sid got his PhD from Princeton and spent a few years at Berkeley as a postdoctoral fellow before moving to UC Irvine and then to his current position at Oxford. He's been for a number of years. He has made enormous contributions to the field of many-body quantum systems. So this is kind of thinking about how topology plays an increasingly important role in our understanding of solids, how dynamics of many interacting electrons or many interacting atoms can lead to sort of unusual behavior. And he's made lots of, he's had lots of impact in this field of that he'll talk about today, which is sort of what happens when you twist 2D materials and look at sort of the physics in this new two-dimensional platform that has been realized over the last 6-7 years. So without further ado, let me hand over to Sid. And if people have questions, I mean, they can probably please ask at the end. But
no, people happy. I'm happy okay, people interrupt, so I can keep track.
So I
Okay, so thank you very much for the generous introduction, Arun. It's a real pleasure to be here. It's about a decade since I was last here, so it's really nice to come back and connect with old friends and make some new ones. So, before starting, I should say, this is a condensed matter colloquium, and I recognize many of the people here aren't condensed matter physicists. And, I think the attitude of lots of physics to condensed matter can be summed up. There was a lovely quote when the gravitational wave observation was announced. I think one of the quanta editors had a Twitter tweet that said, "Oh, thank God it was gravitational waves. I thought it would be one of these condensed matter things that I'd really have to work to explain why this crap is interesting," right? So I'm hoping that, so that's my job today, is to try and explain to you why, in a world where we have all this richness of beautiful things like gravitational waves, we have beautiful problems in cosmology and particle physics, what I want to try and communicate is why this field of condensed matter physics, and particularly the physics of strong correlations, is an interesting one. And partly I want to do that through the lens of a particular new class of materials that for a lot of us is allowing us to kind of understand why we fell in love with that subject in the first place. So hopefully I'll try and be able to communicate some of that excitement to you. So, with that, as Arun said, please interrupt me if something isn't clear. So I want to start off with, biologists are big on central dogmas. So I want to say what the central dogma of condensed matter is, right? And, in some sense, the kind of patron saint of the field is Phil Anderson, who arguably was the first person who took condensed matter and really made it into a field that has its own sort of foundational principles and really brought the ideas together. Phil pointed out in this very, very influential article in Science about just over 50 years ago. What he pointed out was that while we may have a very good understanding of the microscopic rules that make up a chunk of rock, actually understanding what happens to that rock on scales that are far from that microscopic scale can be very challenging. And it's an intellectual endeavor in its own right, because at each new scale, there are new laws that come in that, depend in very opaque ways on the microscopic problem. So this is the fundamental idea that phenomena we study are emergent, and often we can't really understand it ab initio from the microscopic principles. And so what he argued was that research into this is about as fundamental as anything else. And today I want to try and convince you of that, talking about a new field, it's an emerging new field, it's about 5 years old now, of what are called Moiré materials. And I'm going to tie it into the broader theme of research in the field of strongly correlated systems. And before going ahead, I should say that I'm going to summarize the work of many people. Some of it will not be my own because it's a large field. But where I talk about my own work, it's made possible by wonderful collaborations with several students, postdocs, and colleagues over the years. So there's even a partial list has all these names, lots and lots of people. So I'm speaking for many, but any faults in this talk will be mine and not theirs. Okay, so I want to start off with opening up a quantum mechanics textbook. So I talked about strong correlations. So I want to actually pick up possibly the first case you encounter, the question of strong correlations. The first interacting problem you ever solve in quantum mechanics is actually to understand the carbon atom. And the reason is that carbon, we know, what you do is you solve for atomic structure, and you solve for hydrogen-like atoms, and you say, okay, well, carbon has 6 electrons, so we know that we should do it as 1s2, 2s2, 2p2, so much for chemistry. But if you think about it, when you make a 1s state, it's very easy. You say, well, I've got 2 spins up and down. I just squeeze them into a 1s state. That's, after all, the best thing to do. 2s, the same thing. But when I come into 2p, there's a complication. I've got 3 boxes, px, py, and pz orbitals. And I have to choose whether I put in the spins with the same, put in the electrons with the same spin, in which case they'd be forced to occupy different boxes because of Pauli exclusion, or if I put two spins in the same box. And this is, a question that you can't answer at the level of single particle physics. These things are degenerate states. But in fact, Hund pointed out that the second case will clearly have lower Coulomb energy because the electrons don't sit at the same place. So given that electrons like to repel each other, they would be happier. And this is because Pauli, the reason this works, again, is because Pauli told us the wave function should be fully antisymmetric. And if you think of it as a product of a spin piece and an orbital piece, then because the spin is manifestly symmetric, both of them look up, so swapping them doesn't do anything, they have to be antisymmetric in the orbitals. And so that wave function vanishes when electrons get close. So this is one of the rules. And we take this rule and run with it. And thinking about this more generally, we build the entire periodic table. So electron correlations are fundamental to the periodic table, because otherwise we wouldn't know exactly how to fill electrons in atoms. But if you actually go beyond individual atoms and ask about something more complicated, so the next most complicated thing is a metal. And in a metal, you can ask the following question. If I have a Fermi sea of electrons, does it actually get spin polarized by the same mechanism? So here, the problem changes a little bit, because in the previous example, I had a degenerate problem. And I said, if I have up and down versus up and up, there's a very simple calculation you can do. Here, I have to worry about the fact that, when I make the electrons spin polarized, I have to make more up spins and less down spins. And generically, it turns out that costs kinetic energy. There's a kinetic energy penalty you pay for having that many more up spins. That's not gained by having fewer down spins. That roughly has to do with the fact that dispersions typically are convex. They go as p squared. And if you just think of a variational guess that says, let's just take this Hund's rule, the amount of energy you would gain, you actually overestimate the ferromagnetic tendency. And this was pointed out in a really seminal paper by Martin Gutzwiller. And he pointed out that you can actually write down a guess that tells you that electrons can avoid each other without spin polarizing. Essentially, you can write down a wave function for the electrons that says whenever two electrons come close, the wave function vanishes without forcing them to spin polarize. And so, this is not there's lots of work that can be done on this, but the main lesson from this is that, these naive assumptions we make based on simple variational arguments can often go wrong. Problems of correlated electrons are challenging because they're intrinsically a competition between two scales. And so, that introduction was to give you what the problem of strong correlations is, the fundamental question. So what we want to ask is, there are two competing tendencies, right? You write down a Schrodinger equation for electrons. They have a kinetic energy and they have an interaction energy. And the competition between those tells you what matter does on the longest length scales. If the kinetic energy dominates, so the interaction strength is low, then at long distances, you can have itinerant, like wave-like behaviors. The electrons can fly around, they can conduct electricity, sometimes they can superconduct. And so that's something we associate with the metallic or conducting behavior. Conversely, when the interaction strength gets ramped up to be very, very large, then in some sense, the particle-like nature, remember electrons are waves and particles per quantum mechanics, their particle-like nature comes to the fore. And there you can think of them as really being like localized lumps of charge sitting on sites of a lattice or something like that. And so these are what we normally associate with insulating behavior. So this looks good. It looks like we've got an answer. But the problem is most systems don't happily sit at strong or weak coupling. They sit in the middle. And so you say, well, how do I decide? Actually doing this turns out to be very difficult. It goes by the name of the many-body problem. It's exponentially difficult just to say that if I work very hard and solve a problem with, state-of-the-art for many things, about 30 electrons, if you add the 31st electron, then the complexity of the problem doubles. And that's why it's hard to just address these problems computationally, because you're really interested in what happens as that number becomes very, very large. Often things don't settle down at the numbers that you can deal with computationally tractably. So given this kind of complexity of the problem, we have to actually find some organizing principles. And so the field kind of coalesces around thinking about some very broad brushstrokes principles that allows us to make sense of these very, very complicated problems. And so to put this new field in context, I'm going to tell you some old and newer principles that are why we think about these systems the way we do. So the first one is something you might have heard of, which is the Landau paradigm. So Landau said a long time ago that maybe one way to think about different states of matter is if we think about the vacuum, that has all the symmetries you can imagine of nature. But if you think about a rock, it has less symmetry than the vacuum. Often the rock is a crystal, which means it doesn't have perfect translational symmetry. It actually only cares if you translate it by a spacing of the lattice. That's one example. There are lots of other things. And what Landau said is that if you think about all the different ways a lump of rock can have less symmetry than the vacuum, then that gives us an organizing principle to put classify different states of matter. And that's a start to making sense of this very complex, zoo of phases and zoo of phenomena. And so there's sort of lots of stuff to unpack that comes in this paradigm. Essentially, what this says is, if you want to characterize a state of matter in this broken symmetry picture, you can write down something called an order parameter, which just basically says, which way should I point? Because if I break the symmetry of the vacuum, some degree of freedom is pointing in a preferred direction in some abstract sense. And so there's an order parameter. And the physics that this gives you has lots of rich phenomena. So for instance, the fact that there's superconductivity is manifest in long-range order in a certain sense that gives you spectacular phenomena like levitation because of macroscopic phase coherence. You can get sort of very special excitations that are protected, that are sort of carrying, that don't have a gap, that they can rotate a system. They can carry, for instance, heat at no cost through a system, and they're sort of universally protected by broken symmetry called Goldstone modes. And there's a rich set of questions which have to do with what happens when this order parameter, which I can draw here as an arrow, winds around in some topologically non-trivial way. And this kind of comes to the fore when thinking about questions like liquid crystals and all their peculiarities. This is an old idea of broken symmetry and how to think about different states of matter. There's a second principle, which is a little bit different. And this actually goes back to Bloch. So, what I'm going to talk about today are kind of special crystals of matter. And in a crystal, at the very beginning, the electrons don't see every point as exactly the same because the crystal has a periodic array of points, right? It's a periodic system that repeats, but it changes only if you move it by a discrete amount. And so what Bloch pointed out is that fundamentally changes the way the kinetic energy behaves because of the fact that electrons interact not with a constant potential, but some kind of periodic potential that's repeated in space. And that periodicity means that in crystals, rather than have a dispersion that E goes as p squared over 2m that we're used to in free space, electrons have something more complicated. They have some complicated function of their wave vector. And these are what are known as energy bands. And there's one of those for every atom in this every distinct atom in the repeated unit of your crystal has one of these bands. And what's very important is that you can actually ask how many electrons are there in every individual unit cell. So that's something which I'll call the filling that I'll come back to in this talk several times, and I'll call it mu. And why this filling is important is because when crystals form these energy bands, sometimes just that forms as a consequence of the electrons interacting with the periodic array of sites in the crystal. And sometimes that's enough to make a system insulating. And it turns out those insulators are called band insulators because their energy bands themselves know about the system being insulating. And there's a general result that shows that these band insulators are only possible when this number is some very, very special number that's set by the crystal that you give it. And why that's important is because these band insulators, in many ways, are very similar to our vacuum, right? In the sense that if I looked at those band insulators, they have a slightly different dielectric constant, they have a slightly different permeability, but in every other way, they look like our ordinary vacuum. And effectively, they don't care about the interactions between electrons. They don't matter to that insulator. But anywhere away from these very special values of the filling, you get insulate. If I just wrote down this non-interacting band theory where electrons only talk to the lattice, then you see I'll fill up electronic states, but then I'm left over with, the chemical potential lies in the middle of one of these bands, or the Fermi energy lies in the middle of one of these bands, and I can easily excite electrons from unfilled to empty states. So the only reason they're sort of a discrete set of points here is I've taken a finite system. If I have an infinite system, it can create excitations at arbitrarily low energies. So if a system like this becomes insulating, it has to be as a consequence of interactions between the electrons. It can't be because they just talk to a periodic lattice. And these insulators are very special in a certain concrete way. They're called correlated insulators or Mott insulators. And it turns out that they have to break a symmetry or have some other more subtle topological properties. But the most important thing from our point of view is they cannot be understood without invoking the fact that electrons interact with each other, right? And so I want to piece these two things together. I want to look for new states of matter, let's say just looking at states with interesting broken symmetries. And I want to do that in a crystal. But most crystals, if I grow stoichiometric things, often sit at something like this. So I want to start off and add charges to get a situation like this, where in order for the system to do something interesting like become an insulator, it has to break a symmetry. So what I have to do is change this number, right? This number, which is counting how many electrons are there in each unit cell. So is the rule of the game clear? I want to see interesting phenomena. And if I tie these two ideas together, to see those, I have to be able to add charge. And that means that I need to change the density by order an electron in a unit cell. And if you think about the lattice spacing of typical crystals, that's adding or subtracting an electron per third of a nanometer in the system. Okay, so how do we do this? And that will be kind of the route into these new classes of materials. So this is a challenge. So for traditional materials, you need to grow a new sample for each new filling because you do it by alloying to compounds or something like that. And that's a difficult thing. The time scale for this is measured in a very special unit called GSY. Does anybody know what GSY is as a unit? It's graduate student years, exactly, right? Or GSMs if you're lucky, but often GSYs. This is a hard problem, right? Because you've got to, it works if you have infinite funding and 100 grad students, but it's not a great way to spend your life if you really have to do this. It's very difficult to do. I mean, there's some experiments for which is unavoidable, but it is a very difficult challenge. And, in 3D systems, you have no other choice. You have to do this. It's very difficult to do anything else. But in 2 dimensions, there's seemingly a different route. And that is because a 2-dimensional material can form one arm or one sheet of a parallel plate capacitor. So that's what I've drawn over here. So literally, I take a 2-dimensional material. I have a gate plane that I think of as being grounded. And let's think of some numbers. You can get these layers to within about 10 nanometers of each other. It's possible. You have a dielectric constant. The kind of materials you use as dielectric spacer layers typically have a dielectric constant of between 5 to 10. And if you want to keep doing physics and not do chemistry by accident, like chemically change the sample, you can put about a volt or 2. This is just order of magnitude estimates. So given these numbers, you can ask the question, how much can I change the filling? So there's a straightforward calculation because I want to calculate the charge density, but I know that the total charge is just the capacitance times the voltage over the area. Capacitance of a parallel plate capacitor is just the dielectric constant times the area over the spacing. And so I get this nice formula. And if I put in D, E, and V, I get that density is about an electron in a square of side 10 nanometers. Okay? But if you look at the number I put earlier, that's about a 1,000th of an electron in a unit cell. So you're pushing on this sample. You want to add charge to it, but you're not rushing up against the unit cell ever. Right? So it seems like this is completely doomed. We can't do anything. So this seems like it's out. You really can't do this. You have to grow new samples. So what you can do is something different. You could say, okay, what I could imagine doing is if I'm limited to changing the electron density by this amount, maybe I can find some length scale that's about 10 nanometers in a material. So where could that length scale come from? Okay, so that's going to be the story of this talk. But first, there's an old version of this story that there is a length scale that electrons have if you put them in a magnetic field. So in a magnetic field, electrons classically do circular orbits, right? They see a Lorentz force. Again, think of them as 2-dimensional electrons. They can't fly off in another plane. So they move in a circle. But quantum mechanics tells us there's a wave function associated with that, and wave functions pick up phases in magnetic fields. So if you want to think about that wave function to be sensible, the phase they pick up is given by counting, it's essentially the flux through the loop that they enclose, measured in units of this quantity E over h bar c, which is a kind of fundamental unit of flux. It's called the quantum of flux. So, or rather, h bar c over E is the quantum of flux. So this quantity here measures the flux in units of the flux quantum. And I need this to be a multiple of 2 pi, because otherwise the wave function would destructively interfere with itself in the circle, and the electronic state wouldn't be sensible. And so this defines a new unit cell, and that gives you a length scale. And this length scale, called the magnetic length, turns out to be about 10 nanometers at 7 Tesla. So my thought experiment is the following. If I have a sample that I can gate conveniently, I put it in a magnetic field about around 7 Tesla in that ballpark, and I sweep the charge, I should see something interesting happening. That's my prediction. Of course, this is not how it was historically discovered, but conceptually, based on the story I've told you, you should see something spectacular if I take a system and stick it at 10, take it and stick it in a 7 Tesla field, a 2-dimensional electron gas. And that's a very, very famous effect. It's called the quantum Hall effect. So this is a trace, done about 5 years ago by the Columbia group. And what this is showing you is literally, I think this is graphene in the system. So they take a 2-dimensional sheet of graphene, they pass a current in one direction and measure a voltage drop parallel and perpendicular to the current. So the voltage drop perpendicular to the current is in red and parallel to the current is in blue. So you don't need to take much away from this plot. I'll talk a little bit about it later. But the one thing you should take away is this is possibly one of the richest plots you've ever seen, because every one of these numbers over here is a different phase of matter. So in just this lump of graphene, by putting on a magnetic field, I've got a dozen different several dozen new phases of matter. And every time you see a blue peak in the longitudinal conductivity, you have a quantum phase transition between two distinct phases of matter. So this promise of thinking about new phases and organizing principles and sort of trying to see new states of matter is sort of realized really beautifully, if only I can create this new length scale, right? But this takes a lot of work because you don't have a 7 Tesla field lying around, and that's a particular problem that's been studied to death for many, many years. A full explanation involves topology, has 3 different Nobel Prizes at least have been given for this. It's a story for another day. Okay, but we'd like to do something different, right? So this is an old story. So what I'm going to tell you is a different way of getting similar phenomena, and that has to do with something called the Moiré effect. So I went to XKCD and it gave me this little jingle on the Moiré effect. It's playing off on an old Dean Martin song. But what is this Moiré effect? So the Moiré effect is a word, actually. It's not a name of a person. It's a word from the textile industry. And it essentially has to do with the beating phenomenon between periodic structures, which have a slightly offset period or orientation. So let me give you a one-dimensional example. So in 1D, I can imagine taking 2 periodic potentials. So you've got this red and the blue, and they have almost the same wave vector. They just differ by a little bit. And if I add these 2 together, you see this sort of beat phenomena. But the important thing to see is that even though this is not perfectly periodic, there's an approximate periodicity. I hope you can all see that approximate periodicity coming out of this, right? So it approximately repeats itself. And you can check that this length scale is roughly 2 pi over the difference in distance between, difference in wave vector between these guys. And if this delta is small, that's much, much, much bigger than the microscopic length scale. So this is just a 1D version of a simple calculation. So in 2 dimensions, you can take a 2-dimensional sheet of graphene and do something kind of spectacular. So I've just taken 2 sheets of graphene and stuck them on top. And can everybody see that Moiré effect just pop out at you? So can you see that there's a new periodicity that emerges as I rotate? Is that sort of clear? It's sort of visible that there's a new length scale. So we want to calculate what that scale is. And so the reason you can do this is because these 2D materials, they're very strongly bonded in a plane, but they're held together very weakly by van der Waals forces, which means you can effectively take a piece of Scotch tape, stick it on the thing, pull it out, do it a bunch of times, and eventually, if you're lucky, you'll extract a single atom thick layer. This is actually how graphene was originally exfoliated. You can do this now with much more sophisticated tools, but what you can now do is take 2 layers and stick them on top of each other. And if you have a periodic potential, it's now a 2-dimensional periodic potential. So I won't go through the details of this calculation, but what you want to just look at is the smallest difference. You take K1 and K2 are the same vector, just rotated by a little bit. And there's a calculation we often do, which is what's the difference between 2 vectors of the same magnitude rotated by theta. At small angles, it's just the size of the vector times theta. It's a standard calculation that shows up in scattering, for instance. So if you now say that this K is 2 pi over lattice spacing of about 0.3 nanometers, if you stick an angle of about 1.5 degrees, you get a length scale that's about 10 nanometers. So you might expect that if I take this kind of Moiré system and twist it to some angle in this ballpark, I should see interesting physics if I pass current through it, because it's ripe for the formation of new insulating states of matter. So that's the idea. So we're making new states. We found one way to do it. We're going to try to do it in a different way. And there's another little bit of thing that happens for free, that just like the magnetic field modifies the free electron kinetic energy, this Moiré effect modifies the electronic dispersion, leading to very flat. What I mean by flat is bands where the energy barely depends on the momentum. So they're almost non-dispersing bands, as though their mass has gotten very, very heavy. And that means that the kinetic energy is very weak. And that means that the effect of correlations is enhanced. So I'm doing 2 things. I'm boosting the effect of interactions, which helps insulators. And I'm creating a length scale that allows the system to be commensurate in some nice way. So I can control the system of being insulators. And the neat thing about this is that there are lots of materials now that you can create. There's a zoo of exfoliable materials, which means there's many, many ways to get new physics, because you can take various combinations, stack them on top of each other, play with the twist angles. There's sort of combinatorial possibilities. So I'm going to focus on one possibility, which is in some sense the hydrogen atom of the system, which is twisted bilayer graphene. You could write a whole talk on the Moiré physics of this problem, just the single particle Moiré physics. I won't do that, except to say that it's very special because a single layer of graphene, instead of having a quadratic dispersion like p squared over 2m, has a linearly dispersing electron. That's a special feature of graphene. And so for this material, in a beautiful paper now about 15 years ago, Bistritzer and McDonald predicted that these bands would be almost perfectly flat near a certain magic angle. And so if you put in all the extra degeneracies, so in graphene, the electrons carry a spin, and they have some other physics related to doing with their valley and their sublattice. So these are technical terms, but just think like there are 3 different spin-like variables that the electron can have. And since each spin variable has an up or a down state, there are 8 different flavors the electrons can come in. And this is really a dispersion that's pretty typical in this kind of modeling. And so you see that these bands, this is energy as a function of momentum. And so this is a very, very non-dispersive band. So Bistritzer and McDonald said, look, we don't know what will happen, but we know that if you take graphene and twist it to near this angle, interesting physics should occur. That's what they said. And so it took a long time, but the group of Pablo Herrero at MIT actually did some transport experiments on these systems. And what they found was something rather remarkable. So if you look at this system, you see that what I'm showing you is this axis, the density. I've conveniently relabeled it in terms of filling over here. When you had filling of -4 or 4, so neutrality here is when you're in the middle of those 8 bands. So between -4 and 4, the difference is 8. So whenever your density is between here and here, you're putting your electrons into one of those 8 bands. And if you just looked at that problem I gave you earlier, you would only expect to see the conductivity go to 0 at these 2 points. If it goes to 0 anywhere else, it has to be that interactions are doing something special. And so these mean that these are correlated insulating states, because the single application of band theory tells you the system would have to be a metal. What is even more spectacular is that they found out that if you add charge, if you take this insulator and move away from it a little bit, so you add charge to this new form of insulator, they found something really remarkable. They found a superconductor that you could control with an electric field, because adding charge amounts to just dialing an electric field on your gate. And as you do this, the system becomes superconducting, right? So this is something that people have been after for many years, a superconductor you can tune with the gate. And this has been reproduced now, not in the details. The details phase diagrams differ, but the broad phenomenon has been reproduced in dozens of labs. Many different techniques have been applied in various different materials. And there's a wide range of phenomena that are still being debated to this day. But today, I just want to talk about one question, just to give you a flavor of the kind of interesting research. Full disclosure, this is the question I was involved with answering, so it's very selfish. But I want to say what we found was that, what I told you was that, well, at filling -4 and 4, the fact that the system is insulating is boring. There's nothing interesting going on. But if I look at some samples, you see these things that say CS. What that means is that any naive calculation would tell you the system has to be much more conducting than what it is. If it's a metal, it's a really bad metal. You wouldn't want to make your contacts out of that. Or in many cases, it's insulating. And so this has to be because the electrons are talking to each other very, very strongly. So we want to ask, what are these states? What are these 7 states, and how can we model them? Because they can't be band insulators. They require interactions. And it turns out that there's some subtleties to do with this problem. They look like electrons in a magnetic field, which means that you can't just write down some simple model for this physics. And so that's the question. I'm going to answer that in the remaining few minutes of this talk. So I want to go back to that original problem. So I flagged this picture of electrons in a magnetic field. So let me say what actually happens in that problem. So if you put electrons in a magnetic field and you actually solve the quantum mechanical problem, what you get is one of the world's worst problems in degenerate perturbation theory. You find that the electrons form states that look like harmonic oscillator levels, but they look like they're missing a dimension. These are the energy levels of one-dimensional harmonic oscillator for a 2-dimensional system, which means that there's a gigantic degeneracy. There's one electronic state per quantum of flux threading the sample. But flux is an extensive variable. The quantum of flux is some order 1 number. So that means that if I double the flux in the sample, I double the number of states. So this means that there's an extensive degeneracy. And the filling tells us how bad this many-body degenerate perturbation theory problem is. So it counts the number of electrons, the number of flux quanta. So if I forget about anything else like spin or anything like that, if I have an integer filling, it means, for instance, that the filling is 1, I have 1 electron per flux quantum. So it's easy. I can just fill up all the flux quanta. Electrons are fermions. If I put them in one state, they don't allow another one to come in there. To put another in that same position, I'd have to pay this energy cost, and I don't want to do that. So that's easy. I can write down the ground state. It's a bit like a band insulator. This is called the integer quantum Hall effect. But if I'm at a fraction, so if I have 3 electrons in 9 orbitals, right? So if you had solved this is a degenerate perturbation theory problem. So it's 3 electrons in 9 orbitals. There are 84 possibilities. But you want to figure out what particular linear combination of them gets selected. You have to diagonalize. And now with computers, it's trivial to diagonalize an 84 by 84 matrix, right? When Bob Laughlin did this in sort of 1989, he won a Nobel Prize for diagonalizing that matrix, right? Because he guessed what the answer was. So it turns out that I won't go into the fractional quantum Hall effect. There's a nice intermediate case, though. If I put back spin, so I now have 9 electrons in 9 orbitals, but I still have a problem, because do I make those all up spin? Do I make those all down spin? What do I do? And it turns out that I can go back to Hund's rule, because I've taken away the kinetic energy. The Landau level is degenerate. It looks just like a gigantic atom. It's like doing atomic physics with a number of orbitals that scales with your system size. But Hund's rule is great. I know what to do. I put all the electrons as up spins, because then they can never sit on top of each other. The Coulomb energy is happy. And this turns out a really beautiful old story. It's known as the physics of quantum Hall ferromagnets. It's tied to the emergence of unusual things called skyrmions. It's a very old picture. But people like to recycle old pictures. So when graphene Moiré systems came in, people said, look, this is a system that looks like the Landau level. We have 8 flat bands. And after all, the fact that there are 8 of those bands were related to the fact that you have 8 different flavors. So maybe this problem could be mapped to some big quantum Hall ferromagnet. And so before that, though, I want to say something about how you can look for these quantum Hall ferromagnets. So, in the old days, people had to do very difficult experiments. But in a 2-dimensional system, you can look at quantum Hall ferromagnets in an STM. And this will be important in a second. So I was involved with some work about 5 or 6 years ago, where you have quantum Hall ferromagnets where the flavor is associated with the shape of the electronic wave function. So I said that, you have these different flavors that you can ascribe. You can have them, you can see that, electron with a wave function that's distorted that way versus that way, they look different. Think of them as like orbitals or something like that. They look very different. And it turns out that you can look for that. So these are beautiful STM experiments from the group of Ali Yazdani, which actually looked at a very high magnetic field on the surface of bismuth. And what they saw was, depending on what chemical potential they were at, they could see that the electrons, whenever you put in an impurity, it actually is a local witness for the shape of the electronic orbitals. And they could see that all the electrons wanted to line up in one way or the other. But if they looked at this at high temperatures, you couldn't see this kind of stripiness. So this is sort of telling you that the electrons want to polarize and get these orbital degrees, these flavors to line up. And it turns out that STM is so sensitive that you can actually look at interesting physics at domain walls between these. So topology tells you that the domain wall has a perfectly conducting channel, and you can actually work out how that looks in STM and look at it. So there are 2 things I've introduced here. One of them is there's a picture of broken symmetry for these topological bands. That's very rich. And the second is that the scanning tunneling microscope provides powerful insights whenever that symmetry is associated with something like the shape of the electronic wave function. So keep that, because we're going to use see how that gets modified in this Moiré problem. So these were old ideas. These had to do with a big magnetic field. We're going to ask what happens in the Moiré problem. So people thought that the strong coupling problem of TBG would be some very big quantum Hall ferromagnet. This picture was pulled out of a famous paper that said, oh, this has some very nice symmetry. It's got a U4 cross U4 symmetry, which is some fancy mathematical term that just means that it's a very, very symmetric magnet. It's like a gigantic magnet, which doesn't look like a little vector. It's some huge object that you can then work with. But essentially what they said was, well, that's a special point to get all this symmetry. Maybe we can do perturbation theory about that special point and lower the symmetry and get the physical symmetry out of the problem. And when you do that, they got this thing. And I don't remember, I came in to do physics, and physics is supposed to be simple. So when somebody gives me a list of names like this, my eyes start glazing over. I'm like, why do I need to know all these names? So I looked at this plot and said, this answer doesn't look pretty, because yes, you've given me an answer. It's a beautiful, theoretical idea. But there are just too many answers, right? They've got like a different state. Each of these some different state of matter with different phenomenology. And if you actually take this prediction, which is controlled theoretical calculation, and compare it to experiment, you find that it doesn't work. It gets a lot of stuff wrong about experiment. So when we got into this problem, we said we should be able to do better for 2 reasons. 1, can I avoid alphabet soup? And 2, can I actually figure out an answer that's consistent with experiment? And sort of remarkably, we succeeded. So it turns out that we have to worry that these bands are flat, but they're not actually that flat for a variety of reasons. And really, the problem isn't a strong coupling problem where you can do things exactly. You have to worry about the physics at intermediate coupling, where more subtle things can happen. And if you do that, you think, oh, I add all these new ingredients, surely the answer will get worse. It turns out it gets better. At neutrality, you get something, the system doesn't become an insulator. That's consistent with the experiment. But everywhere away from neutrality, you find a single new state of matter at each of those integers. So rather than the alphabet soup, you just need to learn one alphabet, one set of alphabets, the incommensurate Kekulé spiral. So this is a state of matter. And the reason to learn it is this is seen in experiment. I'm going to tell you what this state is and why you can see it. Okay? So the claim was that there's a very complicated zoo of phenomena, and there's just one very simple answer at the end of it. So let's say there are three parts to this: topology, energetics. Those are things I'll get to in a second. But the most fundamental thing is inter-valley coherence. So I've thrown this word valley around. So what does that mean? Valley just means that, I talk about electrons as though they have some dispersion, and that's true. The electrons in graphene have some kind of linear dispersion. They're Dirac electrons. But the zero of their momentum, from which the point about which they disperse, comes from the corners of a Brillouin zone. And so if you're sitting in the K valley, the electronic wave function has, its momentum space structure has these 3 points. They're actually all the same point in momentum space. And if you're in this other valley, it's these 3 inequivalent points. So they're just different points in momentum space. If you like, the momentum space wave functions, the shapes of these orbitals are different. But if you take each of these things, it's actually very hard to see any pattern in an experiment, because this is all physics in momentum space. A way to think about it is, if I take a plane wave and look at its probability density, you just see a constant everywhere, right? So you can think of this K and the K prime values as plane waves going around a hexagonal unit cell. So, it's like 1 e to the 2 pi over 3, e to the 4 pi over 3, a plane wave like that. When you square it, you just see a constant density. The same with the plane wave going the other way. So what do you need to do to actually see something with a modulation? Plane waves don't have modulation, so what has a modulation? Question to the audience. I'm happy to wait. I teach lots of undergrad classes, so I'm very used to extremely awkward silences. So anyone? So plane waves, if you square them, there's no probability amplitude. So how do I get some modulation of the probability from plane waves? Yeah? What? Atom, exactly, sines and cosines, right? So you can add these things with the phase. And if you add the things with the phase, you basically had a wave that was going around clockwise around your hexagonal unit cell. You had a wave going counterclockwise. And depending on the phase with which you add them, you can make the peaks and troughs line up with any of the atoms that you like. You can, it's threefold symmetric, and it's just going to slosh around. And so that's what happens when you add these. You get a pattern, and this is called a Kekulé pattern, because Kekulé pointed out this kind of distortion is relevant for benzene. And this is it's on the microscopic scale, though. This is on the scale of the microscopic individual layers of graphene. But there's a weird thing, that the topology of these bands mean that this expectation value that tells you that these things are interfering with each other has to vanish somewhere on the global Moiré scale. It can't be uniform everywhere. And so if you combine those two things with some energetics, it turns out that these things wind non-trivially in momentum space on the much larger scale. So there's two scales. There's a microscopic crystal. So those pictures I showed you rotating around, there's a spacing between each small dot. But I hope you saw when the pattern finished its rotation, there was a big emergent length scale. So the physics of the small dot scale looks like this. But the physics of the big dot scale means that this pattern sloshes around, right? And that's something, it turns out it's a new state of matter. It's got a fancy name. But the important thing is, what it says that is in real space, if I look in a region, so this is a picture where if I think of that arrow pointing like this, there's a charge pattern with, blue is positive charge, red is negative charge, and the kind of size of the dot tells you how big the charge density is. And as you go through the system, that pattern gradually rotates in space. So it says that there's a pattern of charges that move in space that rotates slowly as you move through the crystal. And it turns out that's something you can see in STM. You can look at a single region of the sample, measure one of these patterns, move phase coherently over several hundred atoms to this other site over here, measure the pattern and see that it's rotated. I make it sound simple. It took 2 years for the group of Ali Yazdani to do this. But when they do that, they actually what they're measuring is the change of one electron in every 10,000 atoms is deciding to redistribute its charge very gently on a microscopic, angstrom scale. And they're actually sensitive to this in these sort of really spectacular pair of experiments, one from the Princeton and one from the Caltech group. So this actually answers the conundrum of what that state of matter is. It's just a piece of flavor. And just as a flash, I promised to tell you that this field has a future. So one of the things is that we found what this insulator is. And so one thing you can ask is, does it actually tell us anything about the superconductor? And the really remarkable thing is that it's sort of amazingly universal. So the twisted bilayer graphene, which I told you about, is a closely related material, which is trilayer graphene. This is a completely different material in some ways, but it has some similarities. And it turns out this state exists there as well. And in fact, if you do numerical modeling, it exists in a version of it exists in almost every graphene-based Moiré material. And it turns out there's some beautiful experiments done in a group in Switzerland that looks at superconductivity in these materials and says, actually, there are two different types of superconductivity. Just like insulators have broken symmetries, superconductors also have different symmetries. And there's a prediction that there's an experimental observation in other groups as well that suggests that there's two different types of superconductor. And really remarkably, if you look at this, what happens when you add charge to this Kekulé spiral state, it changes its normal state in a way that just lines up exactly where we see two different superconductors. So it's a really interesting suggestion that this is actually something, the state, the father or the parent of the superconductor are these kind of weird spiral orders plus charge added to them. So there's sort of ongoing work to really understand what's going on. Now, not just us, but several groups are trying to understand, can we connect, now that we've got one piece of the puzzle, what this insulator is, can we now explain why the system becomes superconducting? But I just want to say, I was told to kind of close in 40 minutes. I think I'm bang on time, but this is actually just, I gave you one story. So what I tried to do in today's talk is sort of give you an overview of what the field of correlated electrons is about, kind of the idea of looking for new states of matter by playing with materials in clever ways. And I kind of told you that the Moiré setting gives us a new way to access those states of matter because of the fact that we can create a new length scale, and that length scale is really amenable to the kind of tools we have to add and remove charge from a system, which is in some sense the fundamental thing to probe metals and insulators. But that was just one story I told you about. It turns out that because of this combinatorial diversity of Moiré systems, there's a whole class of problems to do with a different type of materials called transition metal dichalcogenides, which are other hexagonal lattice materials where instead of having just carbon, you have a heavy metal, a transition metal, and a chalcogen like sulfur or selenium. You take these and stack them together, and it turns out you can get the fractional quantum Hall effect, but without a magnetic field, just because of the conspiracy of how the electrons talk to each other in strong spin-orbit coupling. You can get tunable systems where they look like the electrons can only move in one dimension. Even though you started out with materials that were nominally two-dimensional, you twist them, and the interference is such that electrons can only move in one dimension. They can't move in the other direction. And so there's sort of very rich physics that happens there. There's sort of, on the more applied side, there's a lot of, in semiconductors, there's beautiful physics to do with excitons, which are bound states of particles and holes. So, in undergraduate quantum mechanics, we often give a problem of positronium, which is what happens if you take a positron and an electron and form a bound state. So you can do that with electrons and holes in a semiconductor. There's really positronium there. And it turns out that in Moiré problems, that actually has some topological properties as well. So that's very interesting. And I gave a seminar yesterday in the condensed matter group, actually inspired a lot by these Moiré problems because they allow us to actually look at matter. So when in a lot of things you can't actually interrogate what's going on because in the optical optical wavelengths don't penetrate deep enough to do things, or STM can't actually only scratches the surface. A 2D material is all surface, so it's really motivating people to look at things with completely new probes that they hadn't thought about before. But this is just an invitation to look at a broader, the fact that there's a whole broad class of questions in this spirit. So let me leave you there and thank you for your attention.